Yo, what's up, guys? We're back with another video, and today we're going to be talking about how to do Lewis structures and what they are. So essentially, a Lewis structure is just the formation of like a compound element, not just a compound, and there's electrons. So basically, like an electron configuration sort of thing. And it will make more sense once I explain it. So essentially, let's say you had X and Y. This would be two electrons that represent them being connected together. And then let's say you had a double bond. This would be four electrons. So essentially, every single line that you see between an element is essentially two electrons. Now let's say for some reason that X and Y had these kind of pairs next to them. Essentially what this is called a lone pair. Each dot represents a single electron. And Lewis structures just show the valence electrons and how they're structured inside of a compound. That's really all it is. And it'll make more sense. So first off, we have some rules for valence structures. First off, these elements, fluorine, oxygen, nitrogen, and carbon all follow the octet rule. This means that no matter what happens, their outer shell with valence electrons always needs to be filled with 8 electrons. They're the only ones that do it, especially fluorine. Fluorine is a bitch. I am so sorry to tell it, but fluorine wants to take everything for herself. It's just crazy. Rule number 2. Always minimize the charge on the middle elements. And you'll see what I mean. We're going to be using an equation called formal charge equation, which is essentially the bonds with other elements minus, it's the total number of valence electrons minus bonds minus the number of lone pairs it has. The reason why is because when we're drawing these Lewis structures, we want to make sure that everything is stabilized and balanced. We don't want anything to seem out of the ordinary, or else it won't be the best Lewis structure. Even though it might be the correct one, it might not be the best one. And I had to find out the hard way because I didn't get a 90 on the quiz for chemistry. I love you, Dr. Martinez. I'm trying to think there's a third rule. Not really. Let's just jump into it. So we're going to have a few examples today. And let's see if I can do these myself, because I do struggle in this. First, let's have the all-important element, water, which is also known as H2O. So essentially, in order to draw the Lewis structure exactly, you have to count up the amount of valence electrons it has. So H only has one electron, and that's its single valence electron. And since it's multiplied by 2, we just multiply by 2. And before we get into it deep, we find the valence electrons by looking at the periodic table and looking at the number up top of here. So it's like 6, 7, 8, something like that. These numbers represent the valence electrons. And that's how you can find them. That's what I'm using for all the compounds we're gonna see. So essentially, we have 2 valence electrons from the H2, and then we have oxygen, which has 6 valence electrons, so we have to add 6. So in total, we're representing 8 valence electrons in a compound of H2O. So essentially, how we do that is we write an O and then an H. So from here, the rule is always use the single bonds first, and then fill out the octet. So essentially, we use 2 hydrogens and then connect it to the oxygen. So that's 2 plus 2 is equal to 4 valence electrons. So we have 4 left. And then we just draw oxygen with the lone pairs. And now we use all the valence electrons. So that is essentially your Lewis structure for H2O. It is just hydrogen connected with a single bond to oxygen. It has this octet rule field. And then it's connected to another hydrogen using a single bond. Essentially, that's how you represent hydrogen in the Lewis structure. Water. And it'll make more sense. It's kind of like a little puzzle to do. It is like a little puzzle. It's really, really fun. And let's go back to that 4 more charge I was talking about. 4 more charge is just the charge of each element inside of a Lewis structure. So how we do that, let's calculate for H. So we know H has 1 valence electron and it has 1 single bond, which means that it's just 1 minus 1, which is equal to 0. And since we know that this H is exactly the same, it's also going to have the same charge of 0. And then for the oxygen, the 4 more charge can be used as 6 valence electrons minus the 2 single bonds it has, minus the amount of lone pairs it has. So the pairs in electrons is 4 electrons because we have 1, 2, 3, 4 in the double pair of electrons, which is a 4 more charge of 0. This is why H2O isn't a polyatomic ion, since it doesn't have a charge, cation or anion. Problem is going to make more sense. Then we have NH3. So essentially we do the same thing. We know hydrogen's only going to have 1 valence electron. Since we have 3 of them, we multiply it by 3. And then nitrogen on the periodic table has a number above it of 5. So in total, this structure also has 8 valence electrons that we need to account for. So then from here, we have the middle atom as nitrogen, H, and H. And from here, we know that hydrogen, and this is very important, hydrogen only needs 1 single bond. And that's enough to fill its octet. So none of this is ever going to exist. Don't ever do that, please. So from here, we've used 3 single bonds, which is 6 valence electrons. But we're still forgetting 2 left. And remember that little trick or that little rule I said that CNOF elements always have to have an octet? Here's what I mean. Since we have 2 more electrons left, we just add those to the extra pair. Boom. So now everything's stabilized. Nitrogen has its full octet. The representation of electrons inside of this compound is done. And that's how you represent NH3 as a Lewis structure. Let's keep moving. Now we have CO2. Essentially, for all these atoms or compounds, what you want to do is you want to have the least electronegative, I think. Least something, I don't know, in the middle. The one that's like not the most, you know what I mean? So essentially we have CO2, so we have C in the middle, with an oxygen on the right side and an oxygen on the left side. And you always want to start with that. So now let's start counting up the valence electrons. C has 4 valence electrons according to the periodic table, and oxygen has 6. So for each one we have to multiply by 6, I'm sorry. So we have 4 plus 6 times 2, which is 12. So in total, this whole compound has 16 valence electrons. So from here, since it is one of those elements where we do have to fill in the octet, and now each oxygen has its own little octet field. But you may notice that carbon doesn't have its own octet field. You might be wondering, whoa, what are we supposed to do now? Do we just give up and cry? And I say, no, you do not give up and cry. You never do that. You always keep on pushing. And here's what we do. Essentially, What these lone pairs essentially mean is that this is the outer shell of the oxygen atom, and that's how many electrons they have. But in reality, since most of these are just gases, and Lewis structures talk about gas, you can share the electrons between them. So you can write another single bond, and then another single bond. So I may have not told you about this at the start, but essentially what this means, what the double bond or the single bond means, is that they're sharing the electrons. So essentially, now each element has its octet rule filled. Since each oxygen is sharing 4 electrons from the double bond, and carbon has 4 double bonds, it has 8 electrons itself, and then oxygen also has the 2 lone pairs, which is 4 electrons, and then 4 plus 4 is 8. So essentially, it does fill out the octet rule, and that's how you represent CO2 as a Lewis structure. Now we're going to get into the interesting part. We're going to have polyatomic ion, NO3. I think it's called nitrate. I don't remember. We have NO3 minus. This minus essentially means that we have to add an electron into the equation for the valence electron. So let's do that. We know nitrogen has 5 valence electrons, plus oxygen, which has 6 valence electrons for each element. So we have to multiply that by 3. And then you add the singular one at the end. So you have 5 plus 6 times 3, which is 18. So that's 23 plus 1, which is 24 valence electrons in total. So from here, what you do is you just write down your NO, 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 and fill in the octet. So now we have to see how many valence electrons we use in the diagram. So we've used 6 valence electrons for each oxygen, and we have 3 of them, which is a total of 18 valence electrons. And then we've used 3 single bonds because we need to connect them. So that's 6 electrons, which is equal to 24 electrons. But again, we see that the octet rule isn't filled. So what do? We remove one of them again, and we make it a double bond. And what's special about it is that you don't have to be specific on a single oxygen atom and say, oh yeah, you always have to have 2 lone pairs and the other ones get to have 3. No, you can actually change it. You can actually make this one the double bond, or make, oh my god, wrong button. Or you can make this one the double bond. So essentially, you can have various Lewis structures that all represent the same thing. Isn't that kind of amazing? You can have different versions of the same structure in the same diagram, and people will still understand what you're talking about. Or they won't, because you're just a complete idiot. Who knows? Anyway, that is how you do the Lewis diagram, Lewis structure for NO3. And the reason why it has a minus is because of the formal charge equation. So let's do the formal charge. First off, let's do this single oxygen that's singled out. So we know that the oxygen has, this one specifically has 6 valence electrons always. It has 4 electrons from lone pairs. So no, actually let's do bonds first. It has 2 bonds. So it's 6 minus 2, which is 4, minus 4 electrons from the lone pairs, which is equal to 0. So this one has a formal charge of 0. So now let's do one of the oxygens that has the 3 lone pairs. We know oxygen is going to have 6 minus 1, which is 5 for the single bond, and then it's going to have minus 6 is equal to negative 1. Wait, so this oxygen has a negative 1 charge, but then this one also has a negative 1 charge. Interesting. So now let's do this nitrogen. We know nitrogen is going to have 5 valence electrons. And since we have to count up each bond, including the double bond, so this counts as 2, we know each bond counts in the formal charge equation. So we have to do 1 plus 1 plus 2, which is 4. So we subtract 5 minus 4, which leaves us with 1. And since we don't have any lone pair electrons, what we do is we just subtract by 0 because we don't have anything. So this is actually a positive 1. And the reason why we get a cation is because when we add up all the formal charges of the elements, we're left with a total charge of -1 for the entire compound. This is how you can see why some elements are polyatomic ions and why some aren't. And we're gonna get there. This is the last example. We have SO4 2 minus. This means that we're gonna have to add 2 electrons to the Lewis structure. So we have S, which I believe is 6 valence electrons, plus 6 times 4 for the oxygens, plus 2. So we have 6 plus 6 times 4, which is 24, 30 plus 2, which is 32 valence electrons. So from here, we do the same thing. We have S as our middleman, O, 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 and O. We fill in the octet. And you can see that for each oxygen, we have 6 electrons from the lone pair. So we have 6 times 4, which is equal to 24. Then we have 4 single bonds. So that's 8 more electrons that we've used, which is 32 valence electrons. Now, we're all good, right? No, hell no, we're not good, bro. We're not good. And here's why. Everything's messed up. Yeah, I'm sorry to tell you about that. No hard feelings, okay? This is technically correct. However, there's a better way. There's a much better way to show this. The reason why we don't just keep it like that is because everything is so destabilized because of the electrons. The formal charges are all off. So remember that rule? Minimize charge of middle atom, the one that connects them all. Well, if we do the formal charge equation for S or for sulfur, yeah, I think it's sulfur. If we do the formal charge for sulfur, we have 6 valence electrons minus 4 single bonds minus 0 electrons from the lone pairs, and we get a charge of +2. And then we look at each oxygen. Since each oxygen has 6 electrons and it's all the same, we can do the same thing for our oxygen. Since valence electrons minus 1 single bond minus the 6 electrons from the lone pairs, which is a charge of -1 for each one. However, you get a total charge of -4, and then it's right, but it's not right at the same time. So here's how we do it. We have the S, O, 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 O. So we know that S has to be minimized, but at the same time, it can't hold any lone pairs of itself because every oxygen needs an octet rule. So what do? You let them share electrons. So now let's check the formal charge of the sulfur. We have sulfur, which has 6 valence electrons, minus every single bond that we have. So that's 1, 2, 3, 4, 5, 6, minus the lone pairs, which is a formal charge of 0. This looks a lot better now. Stay with me. We have these 2 oxygens. So let's calculate the formal charge. We know the formal charge is going to be valence electrons, which is 6, minus the single bonds that it has, which is 2, minus the amount of electrons from the lone pairs, which is 4, which is also equal to 0. So these oxygens have a charge of 0. And obviously, since we calculated it, these have -1. But this is the correct way of showing SO4 2-. This is why whatever this polyatomic ion is a polyatomic ion, because it's an ion. But at the same time, when you draw out the Lewis structure, you get to see how the formal charge is very, 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 very important. And you get to see how most of these compounds are sharing electrons. And you might be wondering, well, you said that the elements need to follow the octet rule. Well, I think S is allowed to expand its octet. So there's some exceptions. You'll learn that in chemistry. Don't be mad at me. But essentially, this is how you do Lewis structures, from the most basic, really, to one of the most confusing ones, especially for me. I didn't understand why formal charges exist, or why we have to draw a Lewis structure specifically. But after seeing how we have to stabilize everything, we have to make everything right, it kind of makes sense to me. So hopefully it made sense to y'all. So this has been Lewis structures. Hopefully, if you stay with me to the end, thank you for watching. This is a very, very complicated video for me. And, I just like making these videos and stuff just to teach people about, random science stuff. So, I thank y'all for watching. If you stayed to the end, congrats. We'll give you a cookie. Thank you for watching. Like, share, subscribe, and goodbye.